Hey everybody, it's Mr. Carr again. Today we're going to be looking at section 1 and 2, still looking at our functions, but we're going to be analyzing graphs and functions, the graphs of functions and our relations here. Okay, so again, we talked about what are functions, some of the key parts about them. Remember, the big definition is every input has exactly one output. We can repeat our outputs, we cannot repeat our inputs. So today we're going to be looking at our graphs of functions so we can find domains, ranges, y-intercepts, and zeros of them. We're also going to do symmetries of graphs and identify whether or not it's an even or an odd function. Okay, so first thing is let's talk about domain and range here. So we have find domain and range of this function. So I'm going to just do it as interval notation. You can possibly do it as inequalities, but I like interval notation because that's what you're going to do more of from here on out. Okay, so again, domain is lowest, like what I said for interval notation is always low to high. So for domain, we're going to analyze this from left to right. For range, we're going to go from bottom to top. Okay, so from left to right, you notice how the graph is going to go this way forever. So if I look to the left, there is no limit. It's going to go on forever. So my domain is going to go to a negative infinity from the lowest possible number all the way to the left. Okay, remember from before, that gets parentheses. To the right, we're stopping right here. And that is 1, 2, 3 in the x direction. It's not going anywhere more to the right. So the highest possible number is 3. And that gets a bracket because we're going to include that as part of our domain. Okay. The range, if I go to the bottom to the top, again, just like before, the bottom is going to go on forever. With this arrow on there, it's going to just keep going forever. It doesn't matter. So that's another negative infinity. The highest it goes, we want to be careful. It's not this point here. Some people get thrown off by that. The highest it goes is up to this spot. So we're looking at 1, 2 in the y direction. So it goes up to a 2 with a bracket on that as well. So again, the questions to ask when you're dealing with a graph for domain and range, how far left does it go? How far right does it go? With range, how low does it go? How towards the bottom? And then where's the top? Okay, that's what we're describing there. No, the answer is already here on this one, but it's a good quick showing of that one. Domain, you notice here, if we go from here, it's -3. It does not exist here. So we do a parentheses there. Here, it exists at this point of this piecewise function, but then it jumps down here, then it goes on forever. So that's why it's a -3 to infinity. For range, the lowest it goes is going to be negative infinity. It goes up to a -1 here. So that's this first interval. And then it has that jump, and it jumps to the value of 1. And that's this part right here. And again, that's against a union because it's two different intervals that creates that. Okay, so finding y-intercepts. Remember, a y-intercept is where the graph crosses the y-axis. Okay, so we want to first identify this from the graph itself. So use the graph of the function x squared minus 4x plus 4 to find the y-intercept. Now, this one we don't really have to approximate because it looks like it's crossing right there. So it's crossing at the point 0.04. So my y-intercept should be the point 0.04. Now, to find it algebraically, here's one key fact that we want to remember. If we're crossing the y-axis, the x value has to be 0. So if I want to find that, I'm going to find f of 0. So f of 0 is equal to 0 squared minus 4 times 0 plus 4. So you notice here 0 squared is 0, 4 times 0 is 0, so f of 0 is just 4. Same thing then. We get y-intercept is at the point 0.04. Okay. Along those lines, use the graph of f of x equals x to the third minus x to approximate its zeros. Okay, zeros are where we cross the x-axis. Don't forget about the other names for that. They include roots, solutions, x-intercepts. Those are all referring to the same thing. So if I look at approximately, I've got 1, 2, 3 different zeros. So it looks like I'm crossing at -1, 0, 0, 0, and 1, 0. That's my approximate. Algebraically, we're going to do this. If I'm crossing there, the key here is that crosses the x-axis, the y value is equal to 0. So that means my output f of x has to be 0. So another way of doing that algebraically would be setting it up this way. 0 is equal to x to the third minus x. I'm going to start with some factoring. I can factor a greatest common factor out of x, so it's x squared minus 1 here. If I set this up as two different equations, I got 0 is equal to x, and then 0 is equal to x squared minus 1. I could solve this out. I could do more factoring if I want, but I'm just going to go ahead and do square root property, because 1 is equal to x squared. And then I square root that, so I get a plus or minus 1 is equal to x. So that's where I get positive and negative 1 for this, and then 0 is there for my third solution. Okay. Test for symmetry. Okay. Graphically, so if we say that something is symmetric with the x-axis, what that means is every point xy exists on the other point as x negative y. So we look at that here, kind of gets this sideways looking parabola, or in this case, I like a sideways absolute value. The two x values are repeated, and we have the same y value but opposite signs. Okay. A graph is symmetric to the y-axis if and only if every y point has negative xy also on the graph. Okay, so you see that here. Same idea as the other one, but instead of going up and down, we're going left and right. Negative x and positive x both go to the same y value here. Okay. The last thing is symmetric to the origin. This is only the case where for every xy value there is, negative x, negative y exists. So if this is a positive xy here, this point exists down here as a negative xy. So let's say, for example, this was 1, 1, then this would be a negative 1 here. Okay. There are ways to test the symmetry using algebra. If we, for example, if we replace every y with the opposite version, it should represent the same equation that you just came up with. If you replace x for negative x, you get as the same thing. You should end up with the same exact equation you started with. That's how you test for x and y symmetry. If you plug in x with a negative x and y with a negative y, that will also get you to the same thing, same equation as where you started. Okay, so we'll see that when we look at some of these other ones. So for example, here, use the graph of the equation to test for symmetry with respect to the x-axis, the y-axis, and the origin. Okay, so when we look at this one here, you notice if I say pick a point like this one and I compare it to this one, that's 1, 1, 2, 3, and then -1, +3. Graphically, this is going to be symmetry or symmetric about the y-axis. Okay, so we're looking at something like this. We have a positive and a negative x that go to the same y value. Okay, algebraically, here's how it works. So if I have y equals x squared plus 2, what I'm going to do is I'm going to take my x value and I'm going to change it out for a negative x value. Okay, so I'm going to call it y1 and y2 just to make sure it's clear that we're talking technically about two different y's. So so we have y2 is equal to negative x squared plus 2. Well, what happens when I square a negative value like this? It's a negative x times a negative x. The negative just goes away. So we end up with x squared plus 2. Same thing as what we started with. That's how we show that it is symmetric about the y-axis. Okay. So take a look at this one. Use the graph of the equation xy equals -6 to test for symmetry here. If it's respect to the x-axis, y-axis, and the origin. Now, graphically, again, I'm going to look at this. I don't see anything here because there's no equivalent point up here, and there's no equivalent point left and right. But if I look at a point like this one, let's see if we can kind of estimate one here. Let's say this is negative. I'm not 100% sure on this one. Let's say right here might be -3, +2. Okay. Yeah, that looks, I'm going to estimate that to be a -3, +2. So that means if I go to a +3 and then -2, it should exist on the graph, which it looks like it does. So graphically, I think it's symmetric about the origin or with respect to the origin. That's what it looks like graphically. Okay, now to confirm that, let's go ahead and we replace both x and y with their opposite values. So if the original equation is xy equals -6, I'm going to replace negative x or x with negative x and y with negative y, and it should still stay the same. Well, again, negative times a negative is a positive, so this just simplifies to xy equals -6. So we're good. That's our proof there. Since the first equation and the last equation are the same, that means that it is symmetrical with respect to the origin. All right. This leads us into our functions and describing them as either even functions or odd functions. Okay. So basically, if functions are with respect to the y-axis, it's called an even function. Remember, every x in the domain, we can plug it in so it looks like this, where f of -x is going to come out to the same function that you started with, f of x. If a function is symmetric to the origin, with respect to the origin, that's going to be an odd function. And remember, this is going to be a little bit different here. If I plug in a value -x, what you're going to get is a complete opposite function from what you originally started with. It's a little bit different from what we showed earlier, where you replace both x and y with their negative numbers. Here, if you plug in a -x, you should get a complete opposite equation. So for example, let's say I have y equals x to the third. Let's make it f of x. Okay, then I plug in f of -x. So that's going to be a -x to the third power. Well, this is an odd power, so it's -x times -x times -x. So I'm going to simplify that as -x to the third power. Well, when you compare this is just the same thing as the other one, but the opposite sign. That's it. So this is a very basic version of something that is symmetric with respect to the origin. All right, so let's take a look at some of these. Here's the graph of the function f of x equals x squared minus 4. Analyze the graph to determine whether it's even, odd, or neither. Okay, so then confirm it algebraically. So when I look at this one, again, if it's even, it has to be symmetric to the y-axis. That's what it looks like here. If we pick a point here, there's that equivalent that's horizontal to it. So I'm going to say it's an even function. Okay, and we're going to confirm that with our algebra here. So what that looks like is this. If we take f of x is x squared minus 4, okay, this one right here, I'm going to replace it with f of -x. Okay, so remember, if I take -x squared, that's -x times a -x. I end up with positive x squared. And look at that. It's the same thing as what I started with. So f of -x is the same as f of x. So that's how we confirmed that it is an even function. Since it's even, our symmetry, it has symmetry, or I should say it's symmetric, symmetric to the y-axis. Or about the y-axis. Okay, so it's symmetric about the y-axis. All right, graph the equation xy equals -6 using a graphing calculator. Analyze the graph to determine whether the function is even, odd, or neither. Now, again, we saw this earlier, so we know that it's going to be symmetric around the origin. I'm just going to jump to that idea. We know that the symmetry is about the origin. I'm going to rewrite xy equals -6 as y equals -6 over x. Okay, I want to make sure that's clear that that is going into that it's more of a function setup versus x times y. So determine whether it's even or odd. I'm going to replace x with a -x. So let's see what happens here. We'll call it y1 and y2. So it's going to be -6 divided by -x. Well, what happens when I divide it negative by negative? My new function is going to be a positive 6 over x. So this is the opposite sign of that. It's the same thing, 6 over x, but one's positive and one's negative. That means it is an odd function. Okay, and that means that, again, it has symmetry with respect to the origin. All right. Okay, graph the function f of x equals x squared minus 4x plus 4 using a graphing calculator. Analyze this graph to determine if this function is even, odd, or neither. Okay, so when we look at this one, again, it looks like we don't have y-axis symmetry because we don't have, like, for example, this point here, or I'll pick this point here. This point here does not exist here. It has to have that same distance there. We don't seem to have origin or symmetry about the origin. Okay, so I'm going to say that this is just based on the graph, it's neither. So the way we confirm that algebraically is we're still going to do the same process. We're going to figure out what is f of negative x and compare that to the original. So that's going to be negative x squared minus 4 times the negative x plus 4. Okay, so f of negative x is equal to a positive x squared. Remember, it's a negative times a negative. But this becomes positive 4x. And when you look at these two, it almost looks like it would be symmetrical about the origin or about the y-axis, except for the fact that this positive is the opposite of that. So we get a little bit of both. We get x squared stayed x squared. Positive 4 stayed positive 4. So those would almost be an even function, but then the negative 4x became a positive 4x. So therefore, it's a neither case. So there is no symmetry at all. So that's why we are done with that problem. Okay. And so it's neither even nor odd because it has no symmetry to it. All right. And that is it for today. So don't forget what we looked at. Probably something brand new is talking about even and odd functions, especially when we look at it graphically and algebraically. Otherwise, we're still just analyzing our graphs and understanding how some of those key parts of our functions today. All right. That's it. Take care, everybody.